Hi everyone. In this video, we're going to learn how to do some basic reasoning beyond what we've seen so far with these inductive propositions. At this point, you might have suspected, well, look, we're using the same inductive keyword to define these inductive propositions as we did to define inductive data types. And okay, they're different. One is evidence for propositions that we'd like to prove, and the other is constructors for data that we'd like to manipulate and compute with. But inductive sort of says, oh, this is the exclusive list of the constructors, this is the only way to build things. In principle, these ought to be in common. Can we do case analysis on these things? What about even induction? In this video, we're just going to do case analysis. We'll get to induction soon. But it is totally the case that you can conclude what I've highlighted here. If you have evidence E for the assertion that EVN for some n, then look, that evidence really can only have one of two shapes because there's only two constructors, right? Now, just like for data types, you can write functions that produce, that do interesting behaviors, but they're really, any function on NAT ultimately is only producing O's and S's. Similarly, any proof we do about EV is really just using EV0 and EVSS under the hood. Those are the only pieces. So, if you know EVN, then either E was proved using EV0 and you can conclude N is 0. Or you have EVN and it was proved using EVSS. So then N is S of S of some N prime, where we also have E prime evidence that N prime is even, right? In a sense, we ought to be able to invert the inference rule. And it's true, we can. The way that we'll do it is just using conventional case analysis. Let me show you. Suppose we have a natural number N, and we know that N is even. We'd like to know that either N is equal to 0, or there's some N prime, N is equal to successor of that N prime, and that N prime is even. How will we know this? We're going to go by cases on the way that we derived EVN. We're going to ask Coq, look, you've got this beautiful proof of this inductive proposition EVN. Could you tell me what shape it is? It has to be one of two constructors, either EV0 or EVSS. So I'll say destruct E, and now I have an as pattern. What have I listed here in the as pattern? The arguments of the various constructors. EV0 has no arguments. EVSS takes 2, N prime, the double predecessor, and E prime, evidence that N prime is even. With that in hand, let's see the cases that we get. Okay, we get 2 subgoals. That's a good sign. There were 2 constructors. What happens here? Well, now we have our choice. We could either prove 0 equals 0, seems strong, or there exists some N prime such that 0 equals S of N prime. I'm not into it. I don't like it. I don't like the 0 equals successor of anything. It seems like a bad plan. Let's go to the left. 0 equals 0. You love to see it. Okay, that was the case where E was proved using EV0, and then we were able to say, okay, great. Well, in that case, N is equal to 0. No big deal. What if E was proved using EVSS? Okay, well then there must exist some N prime that's a NAT, and that N prime has to be even. We have to have evidence for that via E prime. But in that case, let's take the right path. We need to find some N prime 0. Great name, Coq, love it. Yeah, you did great work there. We need to find some N prime 0 such that S of N prime is equal to S of N prime 0. Okay, well, I think N prime's a strong candidate there. Let's see what happens. Exists N prime? Okay, this is straightforward. On the left-hand side, it's reflexivity. On the right-hand side, we just use our assumption. Beautiful. So now we have this lovely lemma that neatly characterizes what we know when a number is even. Okay. And in fact, we could, if we wanted to, strengthen this into an if and only if. Here's a quiz. You don't yet have the tools to answer this necessarily, but I want you to think about it, just as a prompt. Suppose you're in this world. We've seen how inversion works, how destruct works. I want you to think about how this nonsensical, this contradictory situation might get resolved, not revolved. Turn it around in your hands. So you have evidence that some natural number n is even, but you also know that n is equal to 1. And you need to prove something you're not going to get. True is equal to false. Okay, so you're in a bad news bears kind of situation. What do you need to do to prove this goal? Because you can. So I ask, do you need destruct alone? Do you need discriminate? Do you need both? Or are you stuck? And this is a cruel question for me to ask. What kind of pedagogy is this? So destruct, well, if if eventually we could destruct this and get a false out, like a capital F false proposition, then just destruct would work because we could blow that up. But that's not how it works. We'll, as we destruct, find out that n equals 0 or that n is successor of something. That seems like a promising route. Then we'd be able to use discriminate to break it up. Discriminate on its own isn't enough, though, because right now there's nothing in this context where there's an obvious contradiction. We've equated two things with different constructors. So discriminate on its own won't do the job either. Destruct and discriminate together do a beautiful job. So here's the proof that I accidentally gave you a glimpse of. Let's see it go. N is a nat. It's even, and it's also equal to 1. Prove that true equals false. It's like, okay, welcome to Crazy Town. Let's go by cases on the evidence that n was even. Well, one form of evidence was EV0. We're in that case now, in which case n is equal to 0. But then our assumption that n equals 1 is pretty well violated, so we can blow it up. On the other hand, maybe it was by way of EVSS. Now here I didn't write a pattern. Maybe a mistake. Maybe this is a little clearer. So there's some n prime and it's even, and successor of n prime is equal to 1. And then you look at that and you say successor of n prime is equal to what? To 1? 1 is successor of 0, full stop. Not going to happen. So the right answer here is both discriminate and destruct. Okay, we can prove this theorem just using destruct. So if a number n is even, then the predecessor of n is even. This might be surprising to you, because doesn't predecessor truncate? Isn't the predecessor of 1, 0? I'm like, yeah, oh wait, it is. So for 1, that's actually totally fine. If you could prove 1 was even, then you could prove 0 was even. Like, all right. Let's see what I mean. We have a natural number n. We need to show that pred of n is even. Let's go by cases. So we're going to do cases on evidence, not on n. If we did cases on n, we would have two cases, 0 and s of n prime. That s of n prime would be super annoying because EV works by doing two successors at once, just like even B did. So by doing cases on evidence, we're only going to consider the good cases. This, you may not understand the full import of this yet, but this ability to only look at the good cases is what is so great about inductive propositions. They let you really specify, hey, these are the things I care about, and then when you do reasoning on them, you only reason about the bits that you cared about. It is a good thing. Okay, let's see how it works. By cases on how we proved that n was even, by cases on the derivation of EVn. Maybe we did it because n was 0, but okay, pred of 0 is 0. So by EV0. Maybe on the other hand, n is equal to successor of some n prime, but those successors and the predecessors cancel, and we knew by assumption that n prime was even. So you might remember this EVPP constructor from the hypothetical quizzes we did earlier. We just showed that EVPP is what is called admissible. That is to say, look, we could have added that constructor, but it's actually just a theorem. So we'll just prove it after the fact. Okay. This can't be handled by destruct. Why not? Let's see. EVS of S of n implies EVn. Let's see what happens. Let n and e be given. By cases, what went wrong? Something's not right here. Okay, so just destruct isn't good enough, but our inversion lemma is perfectly good. If we apply EV inversion, then we get to see, okay, either that's 0 or that. Okay, let's break up H. Okay, the left-hand side's contradictory. What here was an impossible case, we had to prove EV0 for some arbitrary n. Our inversion lemma then says, oh, no, you don't have to worry about this one. Blow it up. Whereas alternatively, we know that n prime is equal to some, there exists some n prime such that n is equal to successor of that number, and that number is even. Okay, let's see what happens. We break it up. Okay, there's n and n prime. Successor of n is equal to successor n prime. N prime is even. Okay. We can use injection to turn that into n equals n prime. We rewrite by that. We use the assumption. Tedious, but our lemma worked. So you might feel your heart sinking in your chest now, being like, So we're gonna have to prove like a dozen of these inversion lemmas, and we're gonna have to do this insane like destruct, injection, rewrite shenanigans all the time? No. This logic and the inversion lemma are all packaged up into one extremely powerful, super cool cock tactic called inversion. Inversion will simultaneously do the work of this inversion lemma saying, hey, here are all the ways I could have found this thing. And then it'll go further and it'll say, look, some of these cases don't make sense. I need to discriminate them and I will blow them up. And then others of these cases induce other equalities that we might care about, right, where we saw that injection. I will conclude those for you automatically. So here is a very nice proof of what was a very ugly proof, or reproof of what was an ugly proof, is what I mean to say. So, okay, we know we have a natural number n, we know EVS of S of S of n, and we say inversion E. Cock, could you please reason by inversion? How could I have found EVS of S of n? And Cock basically looks at this and says, well, okay, I know EV has two constructors. Could be EV0, could be EVSS. EV0 actually doesn't make sense because there's no way for 0 and S of S of n to even unify, right? Prune that one. There's only one way we could have found this. It's by EVSS. And that entails that, okay, there's some n prime, S of S of n prime is equal to S of S of n, and we know n prime is even. So here's the n prime, here's the evenness, here's the equation. So this is everything that we saw earlier in a single go. Fantastic. One other thing you'll notice that it's done, it said, okay, yeah, that n prime is equal to n, and it's substituted everywhere for you. That is, I think, really nice. So, moral of the story, if you have evidence in some inductive proposition and you want to find out what you need to know from it, inversion says, hey, here are the possibilities. Okay, in the next video, very short, I'm going to talk a little bit about some tactics that let you clean up your context, because these patterns are hard to guess. But I'm going to stop here. This video is already too long. Moral of the story, inversion, powerful juju. Okay, talk to you soon.